Okay, so today we want to talk about sector area and a formula that we're going to be able to use to do this. Again, you could do some area arguments based on the area of the whole circle and like a proportion of the central angle of 360. You could do it that way, but we really want to focus on using these new formulas. Earlier we talked about S equals R theta for arc length, and today we're going to look at a sector area formula to find these, where we don't go and use degrees, we use radians. It's going to help us later on with things like angular speed and different questions we have to answer. So just on the picture here, I have a circle with a central angle theta. The arc, the area of the sector is A. It's just the area of that region. And then R is the radius of that circle. So our area, our sector area, A, is given by 1/2 R squared theta. Okay, so, and just like yesterday, we saw with the arc length, is that theta must be in radian measure. I would think, I'm having trouble thinking of an exception. I think anytime you see a formula that just has a theta in it, it should be in radians. I can't think of a case where that's not going to happen. Now, if you have a sine, a cosine, or a tangent of theta, then you have to have the mode of your calculator agree with the way the angle is expressed. But if you just have a naked theta in your formula, and it represents an angle, which it normally will, it's going to have to be in radians for it to work out, because you need that proportion, you need that unitless dimension of a radian. We talked about that yesterday. Because here, if you look, so say your radius is measured in meters, so 1/2 has no unit. This would be meters squared times no unit, so your area would be in meters squared, which makes sense. We're used to seeing that, right? Where if you did it in degrees, you'd get meters squared degrees. That's just kind of weird, right? Just strange. So for our first example here, or I guess it's example 4 on your paper there. It's find the area of the sector of a circle with central angle 60 and a radius of 3 meters. Okay, so again, we're going to use this formula. So if we would use this picture to kind of demonstrate what's going on, our angle here is 60 degrees. The radius here would be 3 meters. Just like we saw with arc length, our first step is to convert theta. We don't want it as 60 degrees. We want it as pi over 3 radians. Now, hopefully that's one that you know. I think a lot of you might still convert to degrees in your head every time you see a radian. The sooner you can let that go, probably the more successful you'll be with this stuff. And then we know the radius is 3 meters. So then the area is 1/2 R squared theta. So we can just plug this in, and we get 1/2 3 squared times pi over 3. And then here we get, we could work this out here. So let's see, 9 pi over 6, if you did it that way, which reduces to be 3 pi over 2. Again, that would be meters squared. It's probably a little awkward to write 3 pi over 2 meters squared. Right? Did anybody work that out on their calculator? Well, I have it, it's 4.71. So I'd say area is approximately 4.71 meters squared. And again, just typing that in. Probably the ideal way to do these is if you're not sure if you should give the exact or the approximate, is to give both. Right? Then you've kind of covered all your bases, right? This is the exact answer where area equals this exact number. This is an approximation. So in this case, if you type 3 pi over 2 in your calculator, it's going to give you this decimal. Now that decimal, because pi is irrational, it won't turn it back into a fraction. So that's kind of what we have going on there. Does that make sense to us for that one? So let's go ahead and try the next one. So for our next one here, we're just using the same equation, we're just doing it a little bit differently here. We have a sector in a circle of radius 25 feet. I went ahead and drew a picture here. Has an area of 125 square feet, and we want to find the central angle. Really drawing a little sketch, it doesn't take long. It's a really nice way to organize your data. I find the less I have to go back and read the whole question and dig out where the numbers go and what they are, the less likely I am to, it seems to make it easier for me. Kind of get a table. It's like a table of values or just a list of variables there. So as we look at this, the area A is going to be 125. I'll leave units off for now. And then R would be 25. And our unknown is theta, which would be our central angle. Let's kind of indicate that with a question mark. So then we can use this formula. Now it's up to you whether, this is just a difference. I would always rather take an equation and rearrange it and solve it for the variable I'm looking for. So this is actually, we might call it a formula, right? Because there's a bunch of variables. I would highly recommend you get it to say theta equals, and then plug your numbers in. It's great practice for like in a science course where you have all these terrible constants or these really unpleasant numbers that you don't want to do. You don't want to do algebra with Avogadro's number, right? It's just a pain. It's so much nicer to rearrange it, type one line in your calculator, call it a day. So what I'm going to do here is I know I want to get theta by itself. And remember, it's being multiplied by a half, so let's go ahead and multiply both sides by 2. Multiply by the reciprocal. So when we do that, we get 2a equals r squared theta. Again, I just multiplied both sides by 2. And then here I want to get theta by itself, so I'll divide both sides by r squared. So 2a over r squared equals theta. And then at this point, to find our central angle, theta is 2 times 125 over 25 squared, which, let's see, I bet we could almost do that. See, that would give us 2/5, right, or 0.4. Now what unit would it be in? Be in radians, right? And if we it's nice at this point too, if you rearrange the formulas, to look at the units, because here you know that area is going to be in feet squared, correct? Square feet. And then here you have feet, but it's being squared. So you have square feet divided by square feet, which cancels out completely. And we know that theta shouldn't have a unit, right? It's unitless. All right, so let's look at actual application problem now with our next example. Okay, so for this next problem here, what we have a little picture was given to us, but we also could make one. So here's the pivot point of the wiper blades, right? We see that here's the path of the bottom of the blade, which I labeled as 14 inches from the pivot point. Obviously, this is not the scale, not even in the ballpark of being the scale. And then this distance from the pivot point to the top of the wiper is 34, right? So the area we're trying to find would be this area in here, correct? So so we have to kind of figure out what this would mean here is this is going to be the large sector, or the sector where R is 34 minus the sector where R is equal to 14 is what we're doing there. We're going to find the difference, right? We're going to find this big entire area, and then we're going to subtract out this smaller sector, and that's going to show us the amount of area that the wiper covers. Okay, so does that follow for everybody there? So again, with this, we have a central angle of 135, but we need to convert that into radians. So 135 times pi over 180, that gives us 3 pi over 4 radians. That's, halfway through the second quadrant, take it to the unit circle. So to do this then, to find our, the actual area, it's going to be 1/2 34 squared times 3 pi over 4, so 1/2 r squared theta for the larger radius. And then we're going to subtract 1/2 14 squared times theta. Let's see, now, I guess we're going to need to use a calculator for this, right? And also, this is an answer that you would want to give as a, you wouldn't want to give it with thetas in it. I was just kind of thinking, if you did notice, if you did have to do it by hand, which would be kind of cruel, because 34 squared seems like a pain having to find that. But notice they both have a common factor of 1/2, and they both have a common factor of 3/4. So a nice trick you could do is say 1/2 3 pi over 4, and then what's left is 34 squared minus 14 squared. Does that make sense here? I just factored out a 1/2 from each of them. I factored out a 3 pi over 4 from each of them. Now, to do this, we will get, let's see, 34 squared minus 14 squared is 960. We still are going to get a decimal. I just wanted to show you that's a technique that's not a terrible one to keep in mind. Kind of factor that piece out. So 0.5 times 3 pi divided by 4 times 960 gives us the area swept out is 1,131 approximately. And that would be square inches, correct? Because it was a square inch minus a square inch, so we're left with the square inch. Any questions with that? Okay. Yes?
I did it by doing the large minus the small one. I got something else. I got 960. Or 360 inches.
Let me come check your math. I think that this should
You
work.
also got the same.
Is that as you did?
Yeah.
You did the Lord. Okay, let me go look. Now, the question was, a great question here is, could you just subtract 34 from 14 to get 20, and then just use that in the measurement?
I didn't.
But you didn't. But this is the correct answer. If you get something different, I'm not sure what happened there, but you need to get this whole number calculated, and then subtract this whole number, and make sure you put pi in there. So let me check your calculations. So the question, we figured it out. The question was, the student had left it with pi in there, which is awesome. It's an exact answer, and the exact answer would be the area is 360 pi square inches, which if you check, this and this are the same number. It's just a different way of expressing it. This is actually the exact answer, where what I went ahead and gave is the approximate answer. So yeah, all in agreement. That's how we do sector area. And don't forget too, a sector could be that maybe you've seen those big giant sprinklers where they grow crops or whatever, the big sprinklers. So say you're running a fertilizer through there, you might need it to go around 10 times. So it's not a case where your angles always have to be some portion of a triangle. The angle could be multiple triangles. If you want to go around 10 times, that would be 20 pi radians for your central angle. And if you were calculating how much fertilizer to buy, let's say. So just like we saw with the wheel spinning on the last example.